Okay, in today's lecture, we're going to cover the section 11.7 material on the chain rule. So the chain rule is going to give us a technique for differentiating composite functions, which show up a lot in our applications later in the course. And in order to define the chain rule, we first need to review what composite functions are. So if f and g are two functions, then we would define the composite function, or sometimes called the composition of f and g, as the function f circle g, or f composed with g of x, as the function f of g of x. So let's think about what this composite function is doing. So if we have some set of variables, let's say x, we can apply some function g to that set, and if we look at the value assigned to the variable x by the function g, we have a element of a new set called g of x. Now if we then apply another function, let's call it f, to this new variable g of x, we would have a new element which we would refer to as f of g of x. So the composite function of f and g is the function that we denote as this f composed with g, so it's f with the little circle, g, and it would be the function that takes x directly to the value f of g of x without having to go through the middle step of finding g of x explicitly. So the domain of such a function, f composed with g of x, would be the set of all values of x such that g of x lies within the domain of the function f. So let's look at some examples working with composite functions, and then we'll state the chain rule, which will allow us to differentiate these composite functions. So in our first example, we're given two functions, namely f of x, which is 3x minus 2, and g of x, which is defined as x minus 1 to the fifth. And in part A, we're asked to find the composite function f composed with g of x. Now, by definition, this composite function is defined as f of g of x. So in order to get the rule for this composite function, we take our function f, which was defined as 3x minus 2, but everywhere I have an x, I'm replacing it with the function g of x, which is defined as x minus 1 to the fifth. So taking the variable x in the rule for f and replacing it by g of x, we have 3 times g of x, which was x minus 1 to the fifth, minus 2. So this would be the rule for that composite function. Now in part B, we're asked to find the composition of g with f of x, that is g composed with f of x. So by definition, if I just change the order here, that means that I'm looking at the value of g of f of x. So in this case, we take the function g, and everywhere that I had an x, I replace it with the entire function f of x. So here we would have x, which is now replaced by the function f of x, which is 3x minus 2, then minus 1, all raised to the fifth power. Or simplifying inside of this set of brackets, we would have 3x minus 2 minus 1 leaves us with negative 3 to the fifth power. So this would be the rule for g composed with f of x. So as we can see, if we compare our results from parts A and part B, in general, the composition of f with g is not equal to the composition of G with F. That is, the order of this composition is important. So let's look at some other examples. In this next one, we have the function f of x is the square root of 3x plus 4, and g of x is x squared plus 5x plus 1. So in part A, again, we're asked for f of g of x. So again, we are taking, by definition, the composition of these functions as f of g of x. So taking the function f and replacing all of the variables x by g of x, we have the square root of 3 times g of x, which was x squared plus 5x plus 1, then plus 4. Or simplifying a little bit, if we distribute our constant 3 under the square root, we have 3x squared plus 15x plus 3, and then our plus 4 gives us a total of plus 7. So this would be the rule for f composed with g of x. And in part B, again, we're asked to find g composed with f of x. So by definition, this is g of f of x. So we're taking the function g, and anywhere that we have the variable x, we are replacing it by the entire rule for f of x. So we would have the square root of 3x plus 4, quantity squared, plus 5 times the square root of 3x plus 4, plus 1. Or simplifying this first expression, when we have the square root of 3x plus 4 quantity squared, we have 3x plus 4. Then plus our 5 times the square root of 3x plus 4 plus 1. So then grouping our constant terms together, the plus 4 and plus 1, we're left with 3x plus 5 plus 5 times the square root of 3x plus 4. And again, comparing our answers from parts A and B, we can see that these two functions are not equal to one another. So again, the order of the composition is important. So in our next example, we've got a similar problem, but working in the opposite direction. We're given a function, which is a composition of two functions, and we're told to express that function as a composition of two functions, and note that there may be more than one way to do this. So in part A, we have the function y equals the square root of 4x squared plus 5. So one way that we could do this would be to define a function f of x as the square root of x and g of x as 4x squared plus 5. So then the rule for our function y could be thought of as the composition of f with g of x. That is f of g of x. So the way that I consider creating this composition is by thinking about the rule for my function as consisting of an inner and an outer function. Now here we have the square root of some polynomial, so this expression under the square root is going to be the function g, and then I'm taking the square root of that entire quantity. So the outer function would be the square root function. So this would be one way I could define that composition. Now we mentioned that there's more than one way to do this. So another approach which we could use would be to let the function f of x equal, say, the square root of 4x plus 5. And here I want to take this rule for my function and replace the x in my 4x plus 5 by an x squared. So I want the inner function, which we're going to call g of x, to be x squared. And so we can verify that the function y could be defined as f composed with g of x or f of g of x. So we see here a couple of approaches that we could use to decompose our function as the composition of two functions. And in fact, there's many more ways, actually infinitely many ways that we could express this function y as a composition of two functions. So let's look at another example of this. In part B, we have the function y is 1 over 2x plus 7 raised to the 5th power. So one way that I could think about this as a composition of two functions would be to take f of x as the function 1 over x to the 5th power, and then my inner function, g of x, well, I want to take the variable x and replace it by 2x plus 7. So my inner function, g, will be 2x plus 7. The outer function is 1 over x to the 5th, so y can be thought of as f composed with g of x or f of g of x. Now to illustrate that there are some other ways that we could do this, we could take, for instance, the function f of x as simply 1 over x, in which case, to get the function that we have here, I want to replace my denominator of x with 2x plus 7 to the 5th power. So in this case, g of x could be taken as 2x plus 7 raised to the 5th. And again, y is then defined as the composition of f with g or f of g of x. All right. So here we're reviewing a little bit on composite functions. And in this next part of our section, we will consider the problem of differentiating a composite function. Now, to differentiate a composite function, we make use of a result called the chain rule. Now, the chain rule says if we have two functions f and g, which are differentiable, and we define capital F of x as the composition of f and g, or f of g of x, then the derivative of that composite function, capital F, is defined as f prime, that is the derivative of the outer function, evaluated at g of x, and then multiplied by g prime of x, that is the derivative of the inner function. So the way that I like to remember the chain rule is as the product of the derivative of the outer function and the inner function. Now, if we make use of Leibniz notation for the derivative, if we have y defined as a function f of some variable u, where u is a function of x, and these are both differentiable functions, then the derivative of y with respect to x can be thought of as the product of the derivative of y with respect to u, then multiplied by the derivative of that inner function u with respect to x. So one way that we can remember the chain rule in the case of the Leibniz notation is if we think of these Leibniz notation derivatives dy over du or du over dx as fractions, then we can think about sort of canceling out this differential du. So here, if we think about canceling these terms out, we see that we're left with dy over dx. Now, these aren't actually fractions. That's just sort of a notational tool that we can use to remember this formula for the chain rule. So let's look at some examples making use of this chain rule to differentiate composite functions. So here we're asked to find the derivative of a given function, and in part A, we have y is the square root of 2x to the fourth plus 3, which we can rewrite as 2x to the fourth plus 3 raised to the 1/2 power. So if we think about this function y as a composition of two functions, we could think of it as follows. So let's choose f of x, perhaps to be the square root of x, and g of x, the inner function, to be 2x to the fourth plus 3. So here, y is the composition of f with g of x. So we can decompose this or think about this as a composition of these two functions, as we did in our previous example. And by the chain rule, the derivative of y, that is y prime, would be found by taking the derivative of f, so here that is f prime, and then evaluated at g of x, times the derivative of g of x. So here, let's see what we have. For the derivative of our outer function, f, we'll recall that the derivative of the square root of x is 1 over twice the square root of x. However, we're supposed to evaluate that derivative at g of x. That is, we replace x in the definition of our derivative of that function by g of x. So we would have 1 over twice the square root of 2x to the fourth plus 3. And then we have to multiply by the derivative of our inner function, g. So here, the derivative of g using the power rule would be 8x cubed. So if we want to simplify a little bit, we could rewrite this as 8x cubed divided by twice the square root of 2x to the fourth plus 3. And then we can simplify this ratio 8 divided by 2 as 4x cubed divided by the square root of 2x to the fourth plus 3. So this would be our expression for the derivative of y. So let's consider another one. In part B, we have y is 10 times 3x squared plus 5x to the fourth. So when we look at this, we can recognize this as a composite function, since it has sort of an inner and an outer function. So here we could think about the outer function, f of x, as being 10x to the fourth, and the inner function, g of x, as the function inside of our set of parentheses, here 3x squared plus 5x. So y would be the composition of these two functions, and to differentiate a composite function, we're going to make use of the chain rule. So by using the chain rule, our derivative, y prime, is given by f prime of g of x, that is the derivative of the outer function evaluated at the inner function, times the derivative of that inner function. So here, starting with the derivative of our outer function, f, well, f of x was 10x to the fourth. So using the power rule, we would have 40x to the third, but recall we're replacing x in that derivative by the inner function, g of x, which was shown here. So instead of just 40x to the third, we have 40g of x to the third, where g of x was 3x squared plus 5x to the third. And then on the end, we have to multiply by the derivative of the inner function g, which is shown here. So the derivative of that function is 6x to the first power plus 5. So this would be our expression for the derivative of that composite function. Now, one thing to notice here, and we'll make this a little more precise in just a moment, but when we're taking the derivative of that outer function, rather than write out our work in this full detail, we could think about it in the following way. We know to differentiate our outer function, we're using the power rule, where I take my power of 4 and I bring it out in front of the variable. So I would have 40, and then times this inner function, my 3x squared plus 5x, then raised to the third power. I just decrease the power of x by 1. And then the chain rule says I still have to multiply by the derivative of that inner function, which was 6x plus 5 here. So rather than write out our full detail where we think about y as a composition of two functions f and g, and then make use of the chain rule formally by writing out this definition, we can think of it a little more intuitively, where we bring down that 4 out in front of our inner function, decrease the power by 1, and then multiply by the derivative of that inner function. So that result that we're describing is a theorem which can be called the generalized power rule, which says if we have a differentiable function f, and we define capital F of x as that function raised to the nth power, where n is any real number, then the derivative of capital F of x is given by n times f of x to the n minus 1. So just like we would normally with the power rule, we can bring the exponent n out in front of this expression. And we have n times now the inner function f of x to the n minus 1. But then the chain rule says for this composite function, we have to then multiply by the derivative of our inner function, which is f of x in this case. So this can be thought of as sort of a more general version of the power rule, where we don't just have a variable raised to the nth power, but we have a function being raised to the nth power. So using this generalized power rule, let's consider the following example. So we're asked to find the derivative of the given function, and in part A, we have a polynomial 13x minus 3 raised to the fourth power. So using the chain rule, specifically the generalized power rule, our derivative y prime is given by 4 times the polynomial 13x minus 3 now to the third power, but the chain rule says we still have to multiply by the derivative of our inner function. So the derivative of that inner function, which is a linear function, is simply the slope of our line, 13. Now, if we want to simplify our answer a little bit, we don't have to here. There's nothing in the directions about simplifying our expression. But if we want, we could take our product of 4 and 13 as a single constant out in front of this polynomial. So 4 times 13 is 52, and then we're multiplying by 13x minus 3 to the third power. So let's look at another one. In part B, We have y is -3 times some polynomial to the third power. So using the chain rule, specifically the generalized power rule, we would have -9 when we pull our exponent 3 out in front and multiply by the -3 times our function x to the fourth plus 7x squared, now raised to the second power. And then the chain rule says we still have to multiply by the derivative of this inner function, which is 4x cubed plus 14x. All right, so this would be our derivative y prime. Now in part C, we have f of x is 4 times the square root of a polynomial. So again, as soon as I recognize that this is a composite function, I know I want to make use of the chain rule. And recall that when we're taking the square root of some quantity, we can really think about that as that quantity being raised to the 1/2 power. So now this looks exactly like the examples that we had just done in parts A and B. So using the chain rule or the generalized power rule, we have our derivative f prime of x is equal to, well, when we pull down our constant 1/2 and multiply by the 4 out in front, we have 2 times 2x squared plus 3x. And then when we decrease the power by 1, we have the -1/2 power. And then the chain rule says, since this was a composite function, we still have to multiply by the derivative of the inner function, which is 4x plus 3. So this is our expression for the derivative, or if we want to simplify this a little bit, we could write this as f prime of x is equal to, taking the constant 2 times this 4x plus 3 on the end, we would have 8x plus 6. And then the expression that we have in the middle here, this 2x squared plus 3x to the -1/2, well, remember a negative power we can think of as 1 over that function to the positive power. And then the 1/2 power is the same as the square root of an expression. So that polynomial being raised to the -1/2 is the same as dividing by the square root of our polynomial, 2x squared plus 3x. So this would be the expression for f prime in simplified form. And in part D, we have a similar problem. We've got 1 over some polynomial being raised to the third power. So we could try to make use of the quotient rule together with the generalized power rule or the chain rule. But an easier approach is to recall that 1 over some quantity to the third power is the same as that quantity, 2 minus x to the fourth, raised to the -3rd power. And now our function looks just like the examples that we've just considered, where we're using the generalized power rule. So differentiating g prime of x is equal to -3 times 2 minus x to the fourth. And now when we decrease our power by 1, we have the -4th power. And we still have to multiply by the derivative of the inner function, which would be -4x cubed. Or if we want to simplify a little bit, again, we could consider the product of this -3 with the -4x cubed on the end as a positive 12x cubed. And then this expression in the middle, this 2 minus x to the fourth raised to the -4, is the same as dividing by 2 minus x to the fourth raised to the positive fourth power. So this would be an alternative way to write that expression for our derivative. All right, so a few examples making use of this generalized power rule. So let's look at a couple of others, maybe combining some of the rules that we've been looking at in the last couple of sections. So here we're asked to find the derivative of y, which is 3x plus 5 squared, then multiplied by 2x squared plus 3x to the fourth. So here we're taking a product of two different composite functions. So in order to differentiate, well, we have to make use of the product rule, since y is now the product of two functions. So here we're going to use the product rule, but notice that each of these functions within our product is a composite function. So when I differentiate those terms, I'm going to have to also make use of the chain rule. So here, by using the product and chain rules, the derivative of our function, y prime, is found by first differentiating the first function in your product. So differentiating that first term using the chain rule, I have 2 times 3x plus 5 to the first power. And then when I multiply by the derivative of that inner function, I have 3. Now, after I take the derivative of the first function in my product, I'm supposed to multiply by the second function, which was 2x squared plus 3x, all raised to the fourth power. And then I have to add, recall the product rule says we then add the first function in our product, which was 3x plus 5 squared, and we multiply by the derivative of that second function in our product. Now, in order to differentiate this second function in our product, we've got to make use of the chain rule, or the generalized power rule. So here we would have, for the derivative of the outer function, a 4 times 2x squared plus 3x to the third times the derivative of the inner function, which is 4x plus 3. So we have the following expression for y prime, our derivative. And if we want to simplify this a little bit, because this is in a pretty messy form, we could see if there's any common factors within this expression from y prime that we could factor out. So here I notice that each term in the sum for y prime involves a 3x plus 5 at least to the first power. So I could factor out a 3x plus 5 from both terms. And I see that both terms in the sum for y prime involve a 2x squared plus 3x at least to the third power. So factoring out a 2x squared plus 3x to the third power as well, let's see what we're left with. So if I factor out these terms from the first part of my sum, I'm left with a 2 times 3 times this 2x squared plus 3x to the first power. When I pull out 3 powers from all 4 powers, I'm left with 1 extra power. So I've got 6 for my 2 times 3, and then times a 2x squared plus 3x to the first power. And for the second part of our derivative, when I pull out my 3x plus 5 to the first power from 3x plus 5 squared, I'm left with 1 power of 3x plus 5. And here I've factored out all 3 powers of 2x squared plus 3x. And then on the end, I've got, or what I'm left over with, is a 4 times 4x plus 3. So if we distribute that 4, we have a 16x plus 12. So simplifying a bit further, I have y prime is 3x plus 5 times 2x squared plus 3x to the third times, when we expand inside of the set of square brackets while distributing the constant 6 for the first part, we have 12x squared plus 18x plus, if I expand the product of 3x plus 5 and 16x plus 12, I have a 48x squared plus 116 times x plus 60. Or combining like terms, in that last factor, I have altogether 3x plus 5 times 2x squared plus 3x to the third. And then my 12x squared plus 48x squared is 60x squared. I have then, let's see, a 18x plus 116x, which would give me a 161x, and then plus 60. All right. So here, this would be our expression for y prime, our derivative, in simplified factored form. So we see here that we did a little extra work in simplifying our expression for y prime. Now, our directions in this problem didn't say anything about simplifying, so we could have left our expression in this very first form that we found for the derivative. But as we'll see as we keep moving through the course, it's often useful to simplify your expression for the derivative when we start talking about applications of differentiation. So let's look at another one. In our next example, we are asked for the derivative of y, which is a quotient of two polynomials, where our denominator, we can see, is a composite function. The inner function for our denominator being x minus 3, and the outer function being x squared. So to differentiate a quotient of functions that also involves a composite function, we're going to have to make use of two rules, namely the quotient rule and the chain rule. So by the quotient and chain rules, we have y prime is equal to, well, the first part of the quotient rule is to differentiate the numerator. So the derivative of our numerator is 12x squared minus 1, and then we multiply by the denominator, which was x minus 3 squared. Then we subtract the numerator, which was 4x cubed minus x, times the derivative of our denominator. Now here, we've mentioned that the denominator is a composite function. So in order to differentiate this, we could use the chain rule. So the derivative of the outer function would be 2 times x minus 3 now to the first power, and then multiplying by the derivative of this inner function, we would have a 1. And then the whole thing is being divided by our denominator, which was x minus 3 squared, quantity squared. So let's see what we have. Y prime is equal to 12x squared minus 1 times x minus 3 squared minus, we have a 4x cubed minus x, and then simplifying a little bit, our product of 2 times x minus 3 times 1 We'll just distributing our constant 2, we have 2x minus 6. And then we're dividing by x minus 3 squared squared. Now remember properties of these power functions. If you have a power being raised to a power, you can express this as x minus 3 raised to the product of those powers. So here 2 times 2 would give us the fourth power. Now, if you want, you can simplify in a similar way that we did in the previous example, but here we could also leave our expression for y prime in this form. Since it's a bit tedious to expand the entire numerator and then group like terms. All right.